Now we're going to talk about midsegments in a quadrilateral. So suppose I took the four midpoints of the four sides of the quadrilateral, and I'm going to connect them, then the shape that they make turns out to be a parallelogram. And in this video, we're going to see why. Well, suppose I took the two diagonals of the quadrilateral. Then we have a number of midsegments here. For example, this segment is the midsegment in this triangle with respect to this side. And this is the midsegment in this triangle. Or this is a midsegment in this triangle, and this is a midsegment in this triangle. And so we get a lot of useful properties from that. For example, now we know that this line is parallel to this line, which is parallel to this line. And so this is parallel to this. Similarly, this line is parallel to this line, which is parallel to this line. And so this is parallel to this. This is a quadrilateral in which the two pairs of opposite sides are parallel, and therefore it's a parallelogram. Furthermore, this parallelogram has sides that are half of the lengths of the diagonals in the quadrilateral, because we know from midsegments that this is half of this, and this is half of this. And so these two have equal length, and it equals half of this diagonal. And similarly, this and this have equal lengths, equal to half of the other diagonal. On this picture, I've marked some of the angles that are equal because of the parallel lines. For example, this angle here equals this angle here because this blue line is parallel to this blue line, and analogously for the other marked angles. We can ask ourselves, how can we find the angle of the parallelogram that we got, so this green angle here that I've drawn. And there are a couple ways we can find it. For example, first one is to notice that this line is parallel to this line, and this line is parallel to this line. So the two lines that are defining this green angle can be slided, respectively this one here and this one here, without changing the angle they make, because parallel lines and translation, respectively, preserve the angles. And so the angle between this and this equals the angle between this and this. And so we get this picture. Alternatively, we can think of the fact that in this straight angle, we have the green angle, the angle marked like this, and the angle marked like this. And in this triangle here, the sum of the angles is 180 degrees, and we have the same marked angle, so this angle and this angle, and therefore the third one must equal this one, because the sum of the three angles here is 180 degrees, and the sum of the three angles in the triangle is 180 degrees. So here I constructed the intersection point of the diagonals in the parallelogram, and we know from the properties of the parallelogram that these diagonals intersect each other at a point which is the common midpoint of these two segments. So this segment equals this segment, and this segment equals this segment. It turns out that this point is actually the center of mass of the whole quadrilateral. And so for any quadrilateral, we can construct this point by taking two midpoints on opposite sides, connecting, and then the two midpoints on the other two opposite sides and connecting and intersecting here. And then we have all these properties. We have that this equals this equals this, and by connecting these, the midpoints like that, we have a parallelogram. And this point being the center of mass means that if you cut a piece of cardboard in the shape of this quadrilateral, and you want to put this piece of cardboard on your finger or on the tip of a pencil, and you want it to be stable, to not fall down, just like I've drawn here, the special point that you can use to put on the tip of the pencil is the center of mass, which is exactly this point. And if you do that, then the quadrilateral will be perfectly stable and it would not fall down in any direction. It would just stay on the tip of your pencil. This optional problem is actually one of my favorite problems, so I hope you enjoy it. We have a cyclic quadrilateral here, and we take the midpoints here, 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 and here of its four sides, and we drop perpendiculars from the midpoint to the opposite side of the quadrilateral, like this. And we do this from every midpoint. So from this midpoint, a perpendicular to this side, from this midpoint, a perpendicular to this side, and from this midpoint, a perpendicular to this side. And we need to prove that these four perpendiculars intersect at one single point. And here's the solution. Of course, since we have a circle, it's a really good idea to construct its center, which will be somewhere here. And furthermore, we have that the center lies on the perpendicular bisectors of each of the sides of the quadrilateral. So we have a right angle here, right angle here, right angle here, and right angle here. Now suppose I intersect this perpendicular and this perpendicular at this point here. Notice that this line is perpendicular to this line, and also this line is perpendicular to the same line. Therefore, this line is parallel to this line. And so in this quadrilateral, this pair of opposite sides is parallel. And similarly, this line is perpendicular to this line, which is perpendicular to this line. And so this line and this line are parallel. And so in this quadrilateral, the other two pair of opposite sides, this side and this side, are parallel. And therefore this here is a parallelogram. Now, taking the intersection of the diagonals of this parallelogram, we know that this point is the midpoint of this segment and this segment because of the properties of the parallelogram. But the midpoint of this segment, this looks suspicious, because this is exactly the center of mass of the quadrilateral. You see, we have that this quadrilateral here, defined by the four midpoints, is a parallelogram, and this is one of its diagonals, and the midpoint of any of its diagonals coincides with the midpoint of the other diagonal. And so this point is also the midpoint of the other diagonal. And therefore we get this picture, in which this point here, the center of mass, is the common midpoint of this segment, and also this segment, right? Because this is a parallelogram. And therefore, if we consider a reflection with respect to this point, or central symmetry, we get that this point maps to this point, and this point maps to this point. And therefore, this here is a parallelogram, because remember the properties of the parallelograms. And therefore, this segment is parallel to this segment. But this segment is perpendicular to this segment. And so the parallel one must also be perpendicular to this segment. So essentially what we got is that if we take the line defined by these 2 points, this line is actually perpendicular to this line. And similarly, because this is parallel to this, it follows that this line must also be perpendicular to this line, as this one is perpendicular to this line. And therefore, these are exactly the two perpendiculars that we took in the beginning, and they must pass through this point. So in conclusion, the point where all the four perpendiculars intersect can be constructed by taking the center of the circle, the center of mass of the quadrilateral, and then reflecting one with respect to the other. And that's how we get this point. And we can show that this is actually the intersection point of all these perpendiculars.